Is it just Vishal presenting today? Is that right?
Yes.
Okay.
I think we should start. It's 10 minutes over.
Yes, I think we should start. We're just sitting idle and just like that.
Should we start? Should I start presenting this my screen now?
Yeah.
I think so. We can start.
Sure. So yeah, so you can see my screen, right?
Yes.
Mm-hmm.
Yes.
Okay, got it. Okay, all right. Thank you. So thank you for your time. My name is Vishal Srivastava, and I will be presenting this particular paper just to give you like a very high-level snapshot from this PDF, and then I will jump into the slides. So basically, this paper is titled as Layered Neural Atlases for Consistent Video Editing. Adobe Research is part of this paper, in the author list, and also it is from one of the premier institute, and I guess this is Weizmann Institute of Sciences in Israel, which is one of the top institute there. So I would now go to the slides. Let's see. All right, so layered neural atlases for consistent video editing. So what is the key motivation for this paper? So well, this paper actually talks about how we can allow complex video editing effects not to be achieved by a non-professional or a novice user. So the paper talks about that there are two key challenges when we allow a non-professional or novice user to be able to consistently edit video images. The first one is when in terms of the video images, right? There are so many frames. So how we could when we change in one particular frame, how that particular change is going to be replicated in rest of the other frames in order to maintain that continuity is one of the challenges that the paper talks about. The second one is how the changes that are being made are how are those changes are going to be consistent in temporal sense, right? In terms of the time, particularly when the video is being played. So after identifying these two challenges, the key research question that the paper is able to pose is how we can allow to facilitate the intuitive and temporally consistent editing. Now, when they use a word intuitive, meaning that it is able to understand, when it is kind of replicating, the edits, it is able to understand what is being done, in the place of when it is being replaced in terms of those modifications. I'll talk more about it in the remaining slides. Yeah. So just to give you a context, what this paper talks about is that, as you can see in the left side, you see a input video when this lady is walking by the path. But then on the right side, suppose if you want to, apply certain modifications in the appearance. So, and then it is temporally consistent, and it is also in terms of spatial, right? In terms of the coordinates, in spatial 3D geometrical space, it is consistent too, not just temporarily. So this is what this paper is trying to achieve. So basically mapping back all the changes to the original video frames with moving objects in temporal and spatial variations. And then these video applications made possible by decomposing the foreground and background. I'll talk about it in a second and wrap them back after modifications. What it is basically saying is that you can look at this particular application in two ways, right? The first one is the foreground and the background. So foreground, if it has to be categorized, the lady is in the foreground, and the background, everything else that you can see. So in this case, the changes or modification is applied in the foreground. And what it then does is that it then wraps it back together. It makes the changes in the foreground. It first decomposes the foreground and background, and then it makes the changes in the foreground and then wraps it back up together in order to show the desired change. And this can also happen in a number of ways. Like you can also make changes in the background as well. So for instance, like this bike riding example here, you can see the kid is bike riding, and then in the background, which is the road here, if we are able to decompose the foreground and background, and we can then make changes in the background and then kind of put it together, then we can see the kind of desired effect that we are trying to achieve. And then in the second video here, just to give you the context, here in the background, certain stars are being modified, and then they are kind of put together with the foreground here. And the same way here in the third example, the input video, which kind of shows like a dull background in terms of the we see a boat here, and then the background kind of appears a little bit dull, but then there are modifications being made in the background, and put together, it kind of looks like a modified, like an attractive image. So how does it do it? Like what's the high level? I have tried to make it in a simpler language so that we understand how it is going at the high level, and then I'll go to the details. So basically what it is doing is that it takes the image, which is kind of a combination of a foreground and background, and then it kind of decomposes in the foreground. For instance, like as you can see the bike here in the UV map, it kind of decomposes in the foreground, and then the background, as you can see here, the remaining things. And then whatever modification, then what it does is that it kind of finds out the geometrical coordinate, and then makes the changes which are desired, and then kind of reconstruct the which it calls as the rewrapping of foreground and background, and then put the image together. Just to give you a context of mask RCNN here, we understand how a convolutional neural network works, right? But in terms of the image detection, what algorithm that they have used is this mask regional convolutional neural network. What it basically does is that, so image segmentation, from the image segmentation standpoint, it basically first partitions the digital image into a set of pixels, which is also known as image object, and then the same segmentation is then used to kind of detect the image and its boundaries. So basically, this mask RCNN, what it does is that it kind of creates that artificial boundary, and then within the artificial boundary, it tries to allocate different objects. It assigns a different class for different objects that it is able to see based on the pixel data that it is storing, and on the basis of different class, and then it kind of it understands, or it finds out what that object, which class it belongs to, and then it does the classification like a usual algorithm, but it does it in a very regional manner, so that it kind of looks at different objects in a little bit more classified manner. So what RCNN is utilizing bounding of boxes across the object regions, which then evaluates CNN independently on all the regions of interest to classify images in the correct class. So this is the essentially the algorithm they are using. So the key points in the paper is that it first introduces an end-to-end coordinate MLP, which is nothing but multi-layer perceptron based framework that decomposes and maps a video into a set of layered 2D atlases, or we can call 2D frames. And then it designs several regularization loss terms that encourages atlas interpretability and facilitates easy and consistent video editing via 2D atlas manipulation. And then it demonstrates that how by applying the RCNN, in terms of the image detection and modification, it is able to do the video editing application that this decomposition enables on a complex real world videos with deformation, reflection, and occlusion by um, first decomposing the foreground and background and then rewrapping everything together. So it also talks about like the difference between 2D versus 3D keyframe editing. So as I mentioned in the beginning, that this is basically Adobe is one of the authors in this paper. So they are kind of proponent of 2D approaches because it is computationally less intensive compared to the 3D approaches. And what it basically does is that it looks at the frame to frame only at the 2D level and tries to convert all the 3D frames back into the two-dimensional frame level data, and then kind of ignore some of the irrelevant information which is not required for the 3D. But whereas in 3D approaches, which of course is more computationally intensive, a geometric model of the scene is estimated and edits are then applied in 3D and then mapped back to the video frames. So this particular paper is not on the three-dimensional image editing space. It is essentially in 2D. So how does it do the decomposition of input video? So input video is into a set of layered 2D atlases of frames, and then each video pixel, the method estimates its corresponding 2D coordinate, and it's something I'll talk in a second how it does that. And then what it does is that once it has extracted the corresponding 2D coordinate, whatever edits are our user is wishing to do, it applies those to those 2D coordinate based atlas that it has extracted, and then it lets the multi-layer perceptron to understand the pixels in that particular two-dimensional frame data that it has extracted. And then purely in 2D, as I mentioned, method does not require 3D surrounding, which is kind of, it makes the so once the convolution understands different pixels and different class, and then it kind of builds the model in terms of understanding, and then kind of it lets the the editing and put it back in the wherever foreground and background, and then extracts the pixel level information, and then produces the desired image. So how they basically approached this particular problem is that what they said was that they basically used a neural video layering to represent the video via a set of layered neural 2D atlases, one for each object to be edited and one for the rest of the content which is in the background. And then what they said was that in each pixel in the video, the method computes its corresponding 2D point, as I mentioned, and then it determines the visibility of each matched atlas point via an associated opacity value. So what happens is that in the training phase, it identifies certain opacity value corresponding to those different pixels that it identifies. And then once this mapping is done, then it parameterizes the original video through the set of 2D frames. Yeah. So as I mentioned, first the mapping of network, it takes a pixel location as input and output its corresponding 2D point in each atlas. As you can see here, this particular example. So it's basically, suppose if this particular object needs to be extracted, then it kind of finds out the geometrical coordinate, and it kind of stores that this kind of information in the CNN. And then each pixel location is also fed into the multi-layer perceptron, which outputs the opacity of which atlas at that location. And then after the initial decomposition of the layers, how it does it by bootstrapping the network using rough object mask that can be automatically computed using mask RCNN, which is kind of self-supervised way this particular algorithm works. And with these networks in hand, a reconstructed RGB color. So basically, the RGB color composition is reproduced in each video pixel, which is kind of estimated by the RCNN. So each framework is trained end to end in a self-supervised manner, where the main loss is a reconstruction loss to the. So basically, there are three kind of losses that this paper is talking about, and the in terms of the algorithm, these three losses are minimized, in order to enhance the accuracy of the prediction. So the three type of losses the paper is talking about in terms of minimizing. One is the rigidity loss, which is local structure of objects to be locally rigid as they appear. So basically, in terms of the geometrical coordinates, right? How much variation can we allow in order to for an eye to kind of not able to see any difference geometrically in space, right? So it looks at that. And then consistency loss, consecutive frames of the video to be mapped to the same atlas point. And this deals with the temporal content, so that the variation does not is a consistent in a way that the image does not, the video does not look distorted. And then specificity loss, use of minimal content needed to reconstruct the video, so that when they are kind of converting from 3D to 2D, basically the idea is to not have the irrelevant pixels, otherwise the computation will become very intensive. Now, what the advantage of the approach that the paper is talking about is that it's the space is continuous, fully differentiable. Specifically, paper avoids the need to discretize the atlas to a fixed resolution during training, allowing the network to distribute the content in 2D space as it likes in order to minimize the object. Consequently, the MLP-based atlases lead to a better visual quality and better. This is what the paper is claiming, and it is also saying that unlike prior work that makes the assumption of a static camera or background, paper allows the mapping network to deform space, which leads to atlases that can model complex geometries. Well, I did not see any evidence of that, but this is what the paper is claiming. Finally, the layer decomposition and mapping allows to composite the user address directly with the original video frames. So yeah, so I was able to do that. I think the tool that they propose is pretty user friendly. There are a few limitations of this paper, which is like they mentioned 5 limitations. The first one is that due to the capacity of the used 2D MLP network, the quality of result decreases for long videos, more than 100 frames, which could be a key limitation, particularly in the real life application. The second one is the different random initialization of the network's weights may occasionally result in different solutions. What this means is essentially that due to their rather simpler approach, sometimes what happens is that the outcome may lead to overfitting, which is like the solution may not be the desired solution. So it may result in not a solution which is being expected, and which is a big thing in terms of the simplicity. Although the paper does offer the simplicity, but offer at the cost of a little bit of accuracy. Third, model appearance variation in the video has been observed in repeat applications. Some noise in the foreground atlases have been observed. So when they try to run the model with the same level of data in certain instances, what they saw was that the repeatability of the image was there was some noise in terms of the repeatability of the applications. So another limitation that they mentioned is that an accurate reconstruction of all video elements in a scene is challenging. So which is kind of understandable, and it kind of prioritizes based on what is the most important image that is being extracted and kind of reproduced. And finally, as discussed, it is difficult for the model to faithfully represent complex geometry and extreme deformation with a single foreground layer. So just to keep the simple. So yeah, so paper introduces the first approach, first of its kind approach for neural video unwrapping using an end-to-end optimized atlas-based representation. And paper claims that the paper is first of its kind that provides the frame-by-frame editing framework that is both accessible for beginners and provides a high level of creative control for professionals. Unlike prior work, this method can be used on a wide variety of input videos, and authors demonstrate the advantage of such an approach on a number of useful downstream applications, which some of these applications have shown. People claim that it has the potential to simplify other complicated video processing tasks. So overall, I think the paper is very very promising. It does have some certain challenges in terms of the repeatability and certain noise that the paper is talking about in terms of the limitations, but it kind of it offers like a promising solution. Let me know if you have any questions. Hello?
Can you please explain the opacity part of it, please?
Sure.
Thank you for the presentation. Can you please explain the opacity?
Sure. So basically, as you can see here in this particular image here, right? So for it is creating, it's trying to keep the the object decomposition and rewrapping part as simple as possible in terms of the computational intensivity is concerned. So what basically it is doing is that in terms of when it kind of extracts these coordinates geometrically, and then also temporarily, then it is basically it is assigning based on the gray map pixel data that it is collecting. It is basically assigning depending upon like the kind of image data that it is extracting, how is the in terms of like recreating of those image object, what is the score that needs to be associated in order to be able to recreate that score. So for how it is doing it, basically it is as I mentioned in terms of the losses, right? The three losses basically here. So when it is comparing with the previous data, it is trying to minimize these three losses in order to reproduce the image back after the modification.
Thank you.
I have a question. How sensitive was the scribbling? Because I know when they was talking about people walking, like the self blocking by the other leg, and that was resolved by them scribbling each leg with a different color. I don't know. Did you get a chance to play with that at all?
You mean the code?
Yeah, if you used
I did try. For some reason, I was like, for some reason I was not able to replicate the code. Maybe because of I don't know, maybe the time. Because of certain libraries I was not able to install at my end, but I would love to give it a chance. So yeah, so that's something I plan to do, but I would do that. Yeah.
Okay.
But I have that code, and it's very intuitive. Maybe I can just walk you through how. Unless somebody has another question, I can just kind of walk you through. I have not run it myself, but I kind of understand what's going on here.
Yeah, because it seemed pretty interesting when you can just scribble on a few legs in it.
Right.
I was just curious to see how that worked.
Right. So I would definitely give it a chance. I was struggling in terms of installing some of these libraries, but you essentially how how a typical CNN, right? You basically assign certain number of pooling layers and the frames basically. So as you can see here, they provide certain assignments to different the alpha is here, by the way, the opacity score. So yeah, so basically depending upon the opacity score and the CNN, they define the layers, etc., and then they run it, and then they are able to get those losses, rigidity loss, and minimize it basically on a very high level. I understand it, but I need to go a little bit for the deeper here. They're combining all these losses here. Yep.
Got it.